Moving into mechanistic considerations, the addition of hydrogen bromide to 1333 tetrafluoropropene. So let's see, there's 1333 tetrafluoropropene, so it's 1, 2, 3 carbons, okay? Double bonds between carbon 1 and carbon 2. There's a fluorine on carbon 1 and there's 3 fluorines on carbon 3. Okay, we're going to add HBr to that, results in 2 structural isomers. In each case, we can see we got still 3 carbons. Now we got 3 hydrogens. We did have 2, so the 3rd hydrogen's been added on. Still got 4 fluorines and now the bromine. So we're adding HBr onto this. Now, if we're going to have 2 possible structures, well, then you can either put the bromine on carbon 2 or the bromine on carbon 1. That's the only way you can get 2 structural isomers. Okay, so now mechanistically, well, first of all, of course, that's an electrophilic addition. Mechanistically, which is what we're interested in here, it goes through a carbocation. Okay, so this one here is where the hydrogen goes on to the less substituted carbon, okay, leaving the more substituted carbon 2 with the carbocation on, and the bromide would attack there. Or alternatively, this is where the hydrogen of the HBr goes on to carbon 2, so that means that carbon 1 would be the positive. Okay, now there's 2 compounds are formed in approximately equal amounts in the reaction. You'd expect this one to be more, but they're both approximately equal. Okay, so why is this ratio different to that found in reaction of other alkenes? Well, the only way is because the carbocation intermediates are of approximate equal stability. Now, if we look at these carbocations, right, you've got positive charge on the carbon, and that carbon is not going to want to lose any more electron density, is it? Thus, if you got a fluorine there, you would say it would destabilize this carbon, okay, because the fluorine's trying to suck electron density away from something that really doesn't want to give it. Now, this one here, you've got 3 fluorines on an associated carbon, which are also going to suck lots and lots of electron density away. So what this is kind of indicating is that a CF3 sucks electron density away about as much as an F directly bonded sucks electron density away. Kind of a sneaky one, but a nice introduction to our mechanistic discussions. So a classic electrophilic addition question, propene right there, carbon 1, carbon 2 with a double bond, carbon 3, which I'm just drawing as a big red blob for a methyl. This is a CH3, remember, reacts with hydrogen bromide. There's the little hydrogen, there's the big bromide. Okay, now you start off, you've got lots of electron density around the carbon-carbon double bond and the pi bonds, and so you've got these electrons ready to react with something positive. Here you've got a hydrogen that's slightly positive because this is a nice polar bond. So the electrons say to the hydrogen, would you like to interact with us? At which point the hydrogen says to the bromide, why don't you get lost? So the result is we definitively have a bromide. But then the question is, where does the hydrogen end up bonded? The hydrogen can pop in and bond on carbon 2 here, leaving the positive charge on carbon 1, or alternatively the hydrogen can bond to carbon 1, leaving the positive charge on carbon 2. Okay, now we've got a carbocation intermediate, so it's a carbocation mechanism. Anytime you're dealing with carbocations, one of the primary ideas is that the more substituted the carbon with the positive charge, the better. So primary carbocations are bad, secondary are better, tertiary are awesome. What we have here, the positive charge on carbon 1, is it's a primary carbocation. Carbon 1 only bonds to carbon 2. Here, however, the positive charge is on carbon 2, which bonds to carbon 1 and carbon 3, so it's a secondary carbocation, so it's much more stable. At this stage then, the bromide, which is negative, sees that positive, says, oh, negatives like positives, and so pops on in to give you 2-bromopropane. Okay, it's not a chiral center, even though it might look like it, because the red blob is a methyl group and this is a methyl group. So no R or S, just 2-bromopropane. Why is the product mainly 2-bromopropane rather than 1-bromopropane? Well, where does 1-bromopropane come from? 1-bromopropane comes from if you have the primary carbocation intermediate, where now the bromide will pop in and attack on carbon 1, thus giving you 1-bromopropane. Okay, again, no chirality issues. You've got 2 hydrogens on each of carbon 1 and carbon 2. Okay, 1-bromopropane comes from the much less stable intermediate, so there will be less 1-bromo than 2-bromo. So, alkenes react with hydrogen bromide by electrophilic addition to give brominated alkenes. Okay, by analogy with the reaction of propene with hydrogen bromide, complete the mechanism of the reaction with but2-ine. So you see 1, 2, 3, 4, there's the but, triple bond, so ine, and it starts 2, with hydrogen bromide to give 2-bromo but2-ene. So 1, 2, 3, 4. So starting at carbon 1, there's carbon 2, which sees the start of the double bond, so the 2-ene and the bromo on it. So let's see, let's throw in what we're doing. HBr is going to react. And so we will have the pi bonds, pi electrons come in and attract the hydrogen to form a bond. The hydrogen tells the bromide to get lost. So that means that now we have this structure here in which you kind of drew for us already, although emphasizing the hydrogen here came from the HBr. We got the carbocation on this carbon here plus the bromide, and then the bromide is of course going to pop on into that carbocation to give us the final product, the 2-bromo 2-butene. All hydrocarbons can be burned, but apart from in combustion reaction, alkenes, more reactive than alkanes, draw the mechanism for the reaction between propene and bromine. Same old thing we've done several times, right? There's propene, there's bromine now. So we start off, of course, with the pi electrons going up towards a slightly positive species. Now what happens here is, of course, that the bromine becomes slightly positive, slightly negative, because as it gets close, the electrons here in this bond are going to be repelled by the pi electrons there. So it's inducing a dipole. This stage we see the usual electrons coming from the pi cloud towards slightly positive, telling the slightly negative to get lost. Now, unlike when we've got a hydrogen coming in here, the slightly positive hydrogen, with the bromine, we not only make a bond between the pi electrons and the bromine, but we also have a lone pair from the bromine comes in and makes a bond with another one of the carbons. So we get the bromonium ion there. Lovely, beautiful little species. Now that bromonium ion, of course, is positive, and there's a negative bromide floating around the place, and so now that negative bromide come in and attack. Now it will attack from the bottom because this bromine is here occupying the top, so it's an anti-attack. Now when it does that, you can have this bromine comes in there, attacking quite nicely there, or the bromine came in from the other side, which will give you the enantiomer. We're not going to worry about that too much here. The important thing is to note that bromine attacks from the opposite side, so it's in the anti-conformation when it first forms. Propenal, so now we're talking about an aldehyde, reacts with hydrogen cyanide, right? A nucleophilic addition reaction. Complete the reaction using curly arrows and partial or complete charges as appropriate. So again, it starts us off, there's propenal, okay? We're throwing a cyanide on there to give us this final beautiful product here. So the first thing is always, 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 when you're talking about your C double bond O, the carbonyl reactions, the carbon slightly positive, the oxygen slightly negative. So the nucleophilic addition is where a nucleophile, in other words, something that likes positives, attack. Well, in hydrogen cyanide, it's the Cn- that is the negative that attacks. And so that's going to come up here and attack the carbon. And thus we see the carbon to the C triple bond N bond forming. Now, of course, immediately that's a 5-coordinate species carbon. So the carbon loses the pi electrons from the carbonyl group, which become a lone pair on the oxygen, as shown by that little curly arrow. So now these 2 curly arrows with the attack of cyanide gives us this. Now, of course, you've got the H plus left from the hydrogen cyanide. H plus likes negatives, so that's going to interact with the electrons from the O minus. Very nice simplistic sense here. Some of my organic colleagues would loathe what I've done there, but that ends up with the final product, which I'll change some colors of. There's the OH and there's the CN attacking the carbon. So a species of millipede can protect itself by producing hydrogen cyanide. This poisonous gas is formed by the Mandela nitrile. Notice we have a carbon bonded to a nitrile, bonded to an hydroxide. And so, in other words, a cyanohydrin, using the old words, making benzaldehyde, plus the HCN. Wouldn't that be fun? Anyway, you can do this in reverse direction, draw the mechanism for the reaction between benzaldehyde and cyanide. So there you go. That's our benzaldehyde. It's an carbonyl compound, slightly positive, slightly negative. There's the cyanide, attacks the slightly positive carbon. Electrons move from the pi cloud to the oxygen as a lone pair, so we have that. And then, of course, the H comes in order to give us the OH bond there. And again, this is going to be a nucleophilic addition.